Okay, so this is another test video. Today is going to be a little more complicated of a subject because I'm just testing it out, and so I'm doing stuff that's vaguely interesting to me. It's also good studying for my exam tomorrow. So, the goal of today is to find all conjugacy classes of the alternating group. The normal subgroup of S5. So, note that A5 is a normal subgroup of S5, where A5 is composed of all the even elements of S5. And so what that means is the order of A5 is going to be 1/2 the order of S5, which is just 1/2 5 factorial. So 1/2 and then 5 times 4 times 3 times 2 times 1, and so you get 120. Well, sorry, 120 divided by 2, so it's 60. Okay. So, also, the conjugacy classes of S5 are the same as the cycle types. This is just kind of a theorem that's mentioned in Abstract 1. I think we proved it in Abstract 2, but it's just a thing that we kind of know. And so now we're going to make a cycle type table for S5. So let's see if we do a cycle type here, and then the number of elements here. So you do that. Okay, so the types are just going to be 5, 4, 3, 3 with 2, 2, 2 with 2, 1. And then just for like a check total, which we said should be 120. Okay. Now, the formula for computing these things is you're going to do kind of realize how many elements you could do. So the first one is 5. So this is how you kind of figure out. Like the first entry can have 5 possible elements, then 4 because you don't repeat, times 3 times 2 times 1. And then you can divide it by 5 because like you don't want to kind of double count, essentially. And so when you do this, you get 24. Similarly, for this, you do 5 times 4 times 3 times 2. The last one doesn't matter. Then you divide it by 4, and so you get 30. This one, you'll just do 5 times 4 times 3 divided by 3, and you'll get 20. This one, you're going to do 5 times 4 times 3, and then divide it by 3. And then for the 2 part, you do 2 times 1 divided by 2. And so you actually also get 20. For this one, 5 times 4 divided by 2, get 10. We'll skip this one for now. You'll get 1. Okay, so for this, you have 5 times 4, and then you divide it by 2, like you normally would. For the second part, you do 3 times 2 divided by 2, like you normally would. But if you get a 2 cycle here and a 2 cycle here, they kind of commute because they're disjoint, and so the order doesn't matter, and so you have to multiply this by 1/2 so you don't end up double counting these cycles. And so when you do all of this, you just get 15. Now, 30, 40, 50, 60, 70, 80, then 90, 100, 110, and then that ends up being 120. Okay, you ignore all that adding, that's just for me. So this, you end up getting all the 120 elements. Now, this is all S5, but what we really wanted was A5, and so we have to remember that A5, again, it had all the even elements. And so looking at these cycle types, 5, if the little trick I had was that like the odd numbers are the even ones, because you can rewrite 5 as like 4 2 cycles, I believe. So you get 5, and then 4 is not, and then you get 3, and then this one's not because you have an even, and you'll end up getting a 2 2 and then a 2, which is odd, so that doesn't work. This one also doesn't work because it's just an even, so therefore it's odd, if that makes sense. And so then you get 2 2, and then the identity is even. So point is, this is all like abstract 1 stuff. The starred ones are the even elements, or the even cycle types, and therefore these are the ones in A5, so these are the ones that we will be concerned with. These cycle types are going to be kind of our, almost our conjugacy classes, but not quite that simple. Okay, so now we're going to start using the actual like abstract 2 knowledge. So we're going to use group actions, and we're going to say, let S5 act on the set of 5 cycles in S5 by conjugation. Now, the reason this works is that if you have, so let's say something of the form tau, sigma, tau inverse. So this would be our 5 cycle. This works in a more general sense, but in this example, this would be a 5 cycle, and you're acting on it by conjugation by elements in S5. But when you do that, you always get you'll get something of the form where it's like tau, and then like the first element in sigma, all the way until whatever the last element is of sigma. And so what you end up, what the point is that however many cycle you get here, so if this sigma is an n cycle, then this whole thing is going to be an n cycle. And so when you act on the set of 5 cycles by conjugation, you're going to get a 5 cycle back. And so that means that the necessary group action properties are preserved. And so that's kind of the big thing that we're working with here. Okay, one moment. Okay, another way of actually kind of looking at this is that, again, in S5, elements are conjugate to each other if and only if they're the same cycle type. So that means that this element, in order to kind of equal this element, which is like what we wanted, they have to be the same cycle type. So again, this action works because this conjugation rule. So, okay, hopefully that makes sense. Moving on. So now we're going to look at basically orbits, or the conjugacy classes. So that means that the orbit of any random 5 cycle in S5 is going to be 24, because we said that the cycle types are the same as the conjugacy classes. Well, and since here the orbit, I guess the definition of an orbit is GA, where this is the action of G on A, but in this case, it really should be written like this. And so the orbit in this case is the conjugacy class, and so it's 24 because the conjugacy class is a cycle type. So basically, again, in this instance, the orbit is the conjugacy class, which is the cycle type. And so that means that if you do the order of all of them, they're equal. And so that's where this 24 comes from. Okay, so now, by our ever so present orbit stabilizer theorem, we can kind of rewrite this as such. We'll have, again, this orbit here, but then this is going to be equal to the order of S5 over the order of S5, and then we're using the notation where it's G sub A, so our G is S5, and then our A is the 5 cycles. Now, what does this equal? Well, remember, the stabilizer, hold on. The stabilizer is going to be all of the G and G such that GA, the action of G on A, is equal to A. But in this case, that's GA, G inverse. That's our action equals A. But you can rewrite this as GA equals AG. And since this is with respect to A, this is the same as the centralizer of A. And again, in this case, A is the 5 cycles. So we can rewrite this as the centralizer of the 5 cycles. Again, this all works because the orbit stabilizer theorem and our action is conjugation, which leads to all of this. Okay, great. And so, when you rewrite all of this, you end up getting that 24, which is this orbit part here, equals 120, which is the order of S5. And it's going to be over this, the centralizer, which means that this centralizer has to equal 5, because 120 divided by 5 is what gives you 24. So that means that the centralizer of S5 of 5 has 5 elements, because the order is 5. Well, what are these 5 elements going to be? Well, you know the identity has to be in there, because that will commute with everything. And you know a 5 cycle has to be in there. But we also know that cycle types, if 5 commutes with, if a 5 cycle commutes with itself, then if you square that 5 cycle, it'll also commute. And so you can do that. But you can square this 4 times before reaching the identity. So, because this first one commutes, so that squared will also have to commute. But you can do that 4 times before you even get to the identity. But now we have 5 elements, and so we have the entire centralizer of 5 cycles, which is what we wanted, or at least what we need to get. Now, what we really are trying to find at the end of the day is all the A5 conjugacy classes. But look at this. See if we can kind of use this to kind of figure out this. What you would do to figure out this, the order of the centralizer in A5 of the 5 cycles, is you just take the centralizer of S5 of 5 cycles and just take out all the even elements. But again, the identity is even, and then all 5 cycles are even elements. And so this is actually equal to 5. So it ends up actually equaling the order of the original one. So now if we use a similar action, except instead of all the S5 stuff we're doing, use the A5 stuff, you end up getting this. Again, the orbits, or conjugacy class, if you will. Or excuse me, I'm sorry. So this, kind of just like we did last time, except now with A5. In the order of A5, again, it's half of 120, so it's 60. We just determined that this was 5. So this conjugacy class of 5 cycles in A5 has 12. Well, what does that mean? That means that, again, there are 24 5 cycles, which is 12 times 2. Since this was an arbitrary 5 cycle, that means that A5 has 2 conjugacy classes of 5 cycles, each with 12 elements. And so we notice that unlike S5, where all the cycles end up being the same as the conjugacy class, here the 5 cycles actually divide into 2 conjugacy classes. And so that's like a third of kind of what we want to do, because again, we have those other cycle types to worry about. We looked just now at 5, so that's good. We know the identity is just going to be 1. And so now we have the 3 cycles and the 2 cycles. So let's see if we can do those. They won't be quite as difficult because the methods are very, very, very similar. And so this time, again, we'll use that S5 beginning part. And so we have the order of S5, but now we're going to do the 3 cycles, which is the order of S5 over S5 again with 3 cycles now. Again, you kind of work with the centralizer stuff, and you get 20, which is the number of 3 cycles, is 120 over something. But that something has to be 6, because 120 divided by 6 is 20. And so that means that the centralizer of S5 of 3 is going to have 6 elements. Well, you'll have 1, and then we'll have like our original 2 cycle, call it 1, 2, 3. And then you'll have that squared, which is 1, 3, 2. If you cube it, you'll get back the identity, so you can stop there. But then we can also throw in 4, 5, because that won't mess with 1, 2, 3. It's a disjoint cycle. And then that also means that you can have the 1, 2, 3, 4, 5, as well as 1, 3, 2, 4, 5. So again, we know these 3 just by doing powers. This one because it's disjoint, and then the last 2 because if these are in here, then like their combinations also have to be in there. But again, that's 1, 2, 3, 4, 5, 6 elements, and so we have them all. But again, we want to look at it with regards to A5 now. So again, now we're going to do that a similar action, but now with A5. And so we're going to get this. Okay, the order of A5, again, it's 60. Now, how many of these elements in the centralizer are even? Well, the identity is, this element is, and this element is. The first 3 we know are. 4, 5 is 1, 2 cycle, so it's odd. And then a 3 cycle and a 2 cycle is an even and an odd, and so therefore that's odd. And so these last 3 end up all being odd, but these first 3 are even. And so we have 3 elements here. But that means that this orbits, or conjugacy class, ends up being 20. But we know that there are 23 cycles in A5 and S5. And so that means that we just have one conjugacy class. Of 20 elements with regards to 3 cycles. So right now we have the 5 cycles, which is 12 plus 12, then the identity, and then this one here. And so that means that we just have the 2 cycles, which, although we don't know how the conjugacy classes will divide, we know we'll end up having to equal 15. And then when you add up all these elements, 12 plus 12 is 24, plus 1 is 25, plus 20 is 45, plus 15 is 60, which is the order of A5. And so it should all end up working out. So let's just check these 2 cycles quickly, hopefully. Okay, so again, skipping a lot of steps, we're going to have the, it's S5. Now it's going to be 2 cycles, which is now S5 all over S5 of 2, 2. So it's going to be 120. Actually, that's not the best way to write this. Sorry. This. So it's going to be 15 equals 120 over a number. But that has to be 8. So we know then that the centralizer of S5 of 2 cycles, that order will be 8. Now, there's 2 ways of going about this. One of them requires you to know rules about kind of how cycles work in S5, like disjointness and how to utilize conjugation and stuff like that. And that's probably the best way of doing about it because it really shows that you know what you're talking about. However, I prefer a different method because I think it's a lot more, requires kind of, it's more intuitive, or maybe not so much intuitive, but certainly easier to understand without just kind of being like, oh, I just needed to know that rule and I forgot that rule. Note that what we're going to end up wanting is the order of the centralizer of A6 of 2 cycles. Well, we know that since this is just this part, but all the even cycles, it's going to have to be a subgroup. If you ignore the orders, I mean, it's going to have to be a subgroup of this. But it's also going to have to be a subgroup of A6. And so, by Lagrange, the order of this has to divide both the order of this and this. And so the order of this we know is 8. And the order of this is 60. Well, what numbers divide both 8 and 60? Well, first of all, it's got to be 8 or less. But 8 does not divide 60. 8 does not divide 60. So, what else? Well, the next number that would work that divides them both would be 4. But here's what we have to notice. What we're going to end up having is we're going to have the order of A5 of 2, 2. And it's going to be 60 over some number. But if we pick a number less than 4, then this, so let's say x, where x is less than 4, then we're going to get a number greater than 15. So for example, if we do 3, 60 divided by 3 is 20. But that means that we have more than 15 elements in a conjugacy class. But there's only 15 2-2 cycles, so that's just a contradiction. But we also know that we can't be greater than 4, because the next number that divides both 8 and 60, it would be 8, but then 8 doesn't work, and you can't go above 8 because 8 is here. So, that means that 4 is the only number that works. And so what we end up getting is 60 over 4, which is 15. And so that means that there is one conjugacy class of 2-2 cycles in A5. Okay, and again, checking, we have 2 for the 5 cycles. We have 120 for the 3 cycles, 115 for the 2 slow cycles, which we just showed, and then the identity, which is 60, which is the order of A5, which is exactly kind of like a check to know that we're doing everything right. And so, therefore, we have found all conjugacy classes of A5. And we're done. Woo!